Hello all. Thank you for joining us for the first session of the ARSET webinar series, Remote Sensing of Land Indicators for Sustainable Development Goal 15. My name is Amber McCollum and I will be your instructor today. For this course, we will have 2 sessions each day. Session A will be at 1 to 2 p.m. Eastern, and Session B will be at 10 to 11 p.m. Eastern. Make sure that you've only signed up for and attend one of these session times. We've created 2 sessions to reach our broader international audience. We will have lectures followed by a short question and answer session. You can find all of the course materials listed on the website here, and eventually the link to the homework. We will also have each of our presentation materials available in Spanish, and the presentations are available in the handouts portion of the webinar pod as well today. If there are any additional questions, you can also email me or my colleague Cindy Schmidt at the email addresses listed here. We will have one homework assignment after all 3 sessions, which will be submitted through Google Forms. The link will be available after the final session on the website, and we'll post it in the Q&A box during the final week. To receive credit for homework, you must submit all answers via Google Forms by July 6th, so that will be 2 weeks after the last session. To receive a certificate of completion, you must attend all live webinars and complete the homework. It takes some time to process these certificates, so you can expect to receive them about 3 months after the completion of this course. There's one prerequisite for this course. First, you should know and understand the fundamentals of remote sensing. You can watch our on-demand course listed above, which includes 2 one-hour recorded webinars that you can watch on your own time. As I mentioned previously, you can access all of the course materials on the ARSET website. Each week, you'll be able to find a PDF of the PowerPoint presentation in both English and Spanish, a link to view the recording for each webinar series, and eventually the link to the homework. Please note that in order to view the webinar recordings, you must register. You will automatically be taken to view the recording. Here's an overview of the course agenda. This week we'll be providing a general overview of SDG Goal 15 and the role of remote sensing to address this goal. This week we will first give you a bit more background about the ARSET program, discuss the framework for the SDGs and the organizations involved. Then we will provide an overview of complementary efforts regarding forest conservation. Then we will discuss the state of the world's forests, specifically from an FAO report. Then we will address the role of remote sensing for SDG Goal 15 and provide some examples of the data sources available. So first, we'll provide an overview of ARSET. The Applied Remote Sensing Training Program, or ARSET, is part of NASA's Applied Sciences program. Our goal is to increase the utility of NASA Earth science data for applied resource management professionals, policymakers, and regulatory agencies. ARSET conducts online and in-person trainings in the focus areas of disasters, land management, health and air quality, and water resources. The ARSET team is located at multiple NASA centers and consists of scientists with backgrounds specific to each topic they teach. ARSET has completed over 80 trainings since it began in 2009 and has reached thousands of participants globally. The figure on the left shows a geographic distribution of participants. We've reached over 8,000 people in over 2,000 organizations and 160 countries. Our online trainings are in high demand, especially with international audience and in regions where there is little in situ data or resources available. We have the unique opportunity to engage a large, highly varied audience that has a need for remote sensing, but doesn't know how to incorporate it into their current workflow. So we have different levels of training, from the fundamentals, such as the one you watched as the prerequisite for this course. But we also conduct basic trainings like this one, and more advanced trainings that include hands-on exercises and data analysis. Below are a few examples of the trainings we've conducted in each of these areas. All of the previous ARSET webinars are freely available on the ARSET website. You can search by a specific topic area or view all the webinars here. In order to view past recordings, you will need to enter registration, and then you'll be taken directly to the recording. This helps us keep track of who is viewing the recordings. Okay, so now we will begin with a little bit of an overview of the Sustainable Development Goals. In September 2015, heads of state and government agreed to set the world on a path towards sustainable development through the adoption of the 2030 Agenda for Sustainable Development. This agenda includes 17 SDGs, which sets out quantitative objectives across social, economic, and environmental dimensions of sustainable development. And all of these are to be achieved by 2030. The goals provide a framework for the people, the planet, and prosperity to be implemented by countries and stakeholders acting in a collaborative partnership. There are 17 SDGs accompanied by 169 targets. Targets are defined as aspirational and global, with each government setting its own national target guidelines by the global level of ambition, but taking into account national circumstances. Each government will also decide targets that should be incorporated into national planning, policies, and strategies. A set of indicators and a monitoring framework will also accompany each target and goal. So this webinar series will focus specifically on Goal 15, Life on Land, and within that targets 15.1 and 15.3 and the associated indicators. So you may be asking yourself, what are indicators? Indicators will be the backbone of the monitoring progress towards the SDGs at the local, national, regional, and global levels. A sound indicator framework will turn the SDGs and their targets into management tools to help countries develop implementation strategies and allocate resources accordingly, as well as a report card to measure the progress towards sustainable development. Each level of monitoring requires different types of indicators. These include 100 global monitoring indicators decided upon based on discussions within a large number of national statistics offices. Each country should pick the number and range of complementary national indicators that best suits their need and capacity to collect and analyze data. The full report for these indicators can be found using this link below the image here. Target 15.1 states that by 2020, to ensure the conservation, restoration, and sustainable use of terrestrial and inland freshwater ecosystems and their services, in particular forests, wetlands, mountains, and drylands, in line with obligations under international agreements. The indicator of focus for our next session will be 15.1.1, or forest area as proportion of total land area. The indicator provides a measure of the relative extent of forest in a country. Forest area as percentage of total land area may be used as a rough proxy for the extent to which forests in a country are being conserved or restored, but it's only partially a measure for the extent to which they are sustainably managed. In order to provide a precise definition of the indicator, it's important to understand the definition of forest as well as total land area. According to the Food and Agriculture Organization, a forest is defined as land spanning more than 0.5 hectares with trees higher than 5 meters and a canopy cover of more than 10%, or trees able to reach these thresholds in situ. It does not include land that's predominantly under agricultural or urban use. Total land area is the total surface area of a country less the area covered by inland waters like major rivers and lakes. For the final session, we will focus on Target 15.3, which states by 2030 to combat desertification, restore degraded land and soil, including land affected by desertification, drought and floods, and strive to achieve a land degradation neutral world. This is more related to forest change and degradation. The indicator of focus for this target will be 15.3.1, proportion of land that is degraded over total land area. The measurement unit for this indicator is the spatial extent in hectares or kilometers squared, expressed as the proportion or percentage of land that is degraded over the total area. Land degradation is the reduction or loss of the biological or economic productivity and complexity of rain-fed cropland, irrigated cropland, or range, pasture, forest, and woodlands, resulting from land uses or from a process or combination of processes arising from human use. Land degradation neutrality is a state whereby the amount and quality of land resources necessary to support ecosystem functions and services and to enhance food security remain stable or increase within a specified temporal or spatial scale. The indicator 15.3.1 is derived by summing all of those areas subject to change, whose conditions are considered negative, such as degradation, while using good practice guidance in the measurement and evaluation of changes. And there are 3 sub-indicators: land cover and land cover change, land productivity, and carbon stocks above and below ground. The most common method involves the use of site-based data to assess the accuracy of the sub-indicators that may be derived from Earth observation and geospatial information. There are a variety of organizations involved in the SDGs, with the primary organizations being part of the United Nations, like the UN Statistics Division, the UN Convention to Combat Desertification, the Sustainable Development Solutions Network, and the Food and Agriculture Organization, or the FAO. Additional organizations, such as the IISD, provide support to countries. It reports on international negotiations, conducts research, and engages citizens, businesses, and policymakers on these shared sustainable goals. The IISD has the SDG Knowledge Hub for Information, which we'll talk about later. The Group on Earth Observations, or GEO, is a partnership of more than 100 national governments and in excess of 100 organizations that envisions a future where decisions and actions for the benefit of humankind are informed by a coordinated, comprehensive, and sustained Earth observation network. GEO is working specifically on addressing the SDGs with remote sensing. The Partnership for Sustainable Development Data has the goal of bringing together public and private stakeholders to fill the gaps in knowledge, establish global norms and standards to increase the ease and security of sharing and using data, and to help countries develop more robust strategies for data development. Additionally, many other country ministries and statistical offices work towards meeting these goals. The International Institute for Sustainable Development, or IISD, provides advanced, integrated, multidisciplinary perspectives and real-world solutions to sustainability. The core purpose is to build a single, coherent institution capable of providing integrated solutions to meet these goals. The SDG Knowledge Hub is an online resource center for news and commentary on the implementation of the 2030 Agenda. You can visit the Knowledge Hub at the website shown here and find information specific to each of the SDGs and related events, including information about the organizations involved and recent developments. The IISD develops and applies measurement and assessment tools and processes, including indicators, as well as building capacity to foster engagement between the policymakers and leaders. The UN Statistical Commission, established in 1947, is the highest body of the global statistical system. It brings together chief statisticians from member states all around the world to make decisions for international statistical activities, especially the setting of statistical standards, the development of concepts and methods for the implementation at the national and international level. The Statistics Division has a global SDG indicator database, and here you can select specific indicators and take a look at different countries' data. The global SDG indicators database also presents data for the world as a whole and for various country groupings. So they have things classified as developing regions and developed regions. In 2012, the UN Secretary General Ban Ki-moon launched the UN Sustainable Development Solutions Network, or SDSN, and this is used to mobilize global scientific and technological expertise to promote practical problem solving for the SDGs. It works closely with the United Nations, and it has multiple online courses available via the SDG Academy. So this shows some of those courses available here, and the website is listed above. GEO is a partnership of government institutions, academic and resource institutions, data providers, businesses, engineers, scientists, and experts that aim to integrate Earth observations into decision-making. The GEO community has created the Global Earth Observation System of Systems to better understand observing systems and to share data through existing infrastructure. There are more than 200 million open data resources from more than 150 national and regional providers such as NASA and the ESA, including international organizations such as the World Meteorological Organization and commercial sectors such as Digital Globe. In Earth observations and service for the 2030 SDG agenda, enables contributions from the Earth observing community. The primary purpose of this initiative is to organize and realize the potential of Earth observations and geospatial information for this type of societal benefit. The Food and Agriculture Organization, or FAO, works to achieve food security, to ensure that people have regular access to high-quality food to lead active, healthy lives. The FAO has supported decision makers to create the SDG agenda, and there are 14 thematic areas where the FAO contributes technical knowledge to the open working group for the SDGs. The themes are based on the organization's global goals, such as the eradication of hunger, the elimination of poverty, and the sustainable management and utilization of natural resources. The FAO has generated multiple reports, including the State of the World's Forests, which we will review a little bit here as well. Next, we will discuss some additional related forest conservation efforts. The New York Declaration on Forests is a non-legally binding political declaration that grew out of dialogue among governments, companies, and society. The world leaders have endorsed a global timeline to cut natural forest loss in half by 2020 and to end it by 2030. It also calls for restoring forests and croplands of an area larger than India. Meeting these goals would cut between 4.5 and 8.8 billion tons of carbon pollution each year. And this is about as much as the US emits. The declaration is endorsed by dozens of governments, large companies, and indigenous organizations. The entities endorsing the declaration announced dozens of concrete actions and partnerships. So these actions include things like having commodity traders call for public policies to eliminate deforestation, a pledge by indigenous peoples to protect hundreds of millions of hectares of tropical forests, new commitments from forest country governments to reduce deforestation, bilateral and multilateral programs to pay for reduced deforestation, and new procurement policies for several of the largest forest commodity importer governments. The Bond Challenge is a global effort to bring 150 million hectares of the world's deforested and degraded land into restoration by 2020, and 350 million hectares by 2030. The restoration of this land is in line with the Forest Landscape Restoration Approach, or FLR. This is an ongoing process of retaining ecological functionality and enhancing human well-being across deforested or degraded forest landscapes. The Bond Challenge is not a new global commitment, but rather a practical means for realizing some of these other international commitments. And this includes things like the REDD+ goals. It's an implementation vehicle for national priorities such as water and food security and rural development, while contributing to the achievement of international climate change, biodiversity, and land degradation commitments. The United Nations Collaborative Program on Reducing Emissions from Deforestation and Forest Degradation in Developing Countries, or REDD, was launched in 2008. It incentivizes developing countries to keep forests by offering results-based payments for actions to reduce or remove forest carbon emissions and to enhance forest carbon stocks while contributing to sustainable development. The UN REDD program supports the REDD+ progress, and it began as an effort primarily focused on reducing forest emissions. In 2010, at the COP16, REDD became REDD+ to reflect a few new components that are shown here. So this now includes reducing emissions from deforestation, reducing emission from forest degradation, conservation of forest carbon stocks, sustainable management of forests, and enhancement of forest stocks. So as you can see, there are many related global efforts and supporting organizations tied to forest conservation. So we've just presented a short overview of some of these, but I encourage you all to seek out more information on these various efforts, and for most of them we have the links related on each of those slides. So now I'm going to briefly provide you a little overview of the state of the world's forests. And this primarily comes from a handy report that was recently written by the FAO. This report explored the challenges and opportunities represented by this complex interrelationship between forests, agriculture, and sustainable development. We know that forests and trees support sustainable agriculture, for example, by stabilizing soils and climate and regulating water flows. However, agriculture is still a major driver of deforestation globally. And agricultural, forestry, and land policies are sometimes at odds. The State of the World's Forest 2016 shows that some countries have been able to reconcile the aspirations of these different sectors, increasing agricultural productivity and food security while also halting or reversing deforestation. Integrated land use planning provides an essential strategy framework for balancing these land uses. So planning processes must be participatory because it involves the farmers and rural people who ultimately make the plans, make the decisions to put the plans into practice. This report provides a brief historical review that identifies the relationship between population growth, increased demand for agricultural land, and forest loss, and this dates back thousands of years. The figure on the top shows the proportions of the total land area occupied by agriculture, forests, and other types of land uses in various regions of the world. And this was as of 2010. Notice that forests account for a large portion of land in Europe, North, Central, and South America. Globally, forest area fell by 3.1% from 1990 to 2015. There was a net forest loss of 7 million hectares per year in tropical countries from 2000 to 2010, and a net gain in agricultural land of 6 million hectares per year. The bottom figure here shows that there were net declines in forest area in the tropical climatic domain in each of these 3 5-year periods between 2000 and 2015. In contrast, the net forest area increased in the temperate regions in each of these periods, and there were only relatively minor changes in forest area in the boreal and subtropical climates. So there's a strong correlation between agricultural expansion and deforestation, as shown in dark red regions on this map. These are areas with a net gain in agricultural area and a net loss in forests, primarily in regions like South America, parts of Africa, and Southeast Asia. The greatest net loss of forests and net gain in agricultural land over the period was in the low-income group of countries, where rural populations are growing. The light green regions show a net gain in forests and a net loss in agriculture, and these are primarily in the US, Europe, and Northern Asia. The light red regions show a net loss in both agriculture and forests, and the dark green shows net gain in both of those categories. This figure shows the proportion of total land use change associated with drivers of change on the left, and the net forest area loss associated with those percentages on the right. Large-scale commercial agriculture accounts for over 70% of deforestation in the tropics and subtropics. Underlying factors affecting forest conversion include population growth, changing food consumption patterns, such as changing markets, technological improvements, and active policy interventions, land tenure security, and the governance of land use change. Forest loss in 2010 to 2015, most of which was natural forest loss, was offset primarily by a combination of natural expansion, often in abandoned agricultural land, and the establishment of planted forests. There's an increasing need for countries to address land use change in national policies. So we reviewed many of these policies in those first few slides. However, it's a complex process, and it includes many factors in countries, each with their individual challenges related to forest conservation and food security. As I mentioned in general, forest losses are greater in low-income countries when investments in agriculture and forests are relatively low. Direct public investment is an increasingly focused area in environmental and social protection. And there is increased emphasis on creating enabling environments for private sector investments. So to summarize this report, it really argues for a multi-pronged approach that includes coordinating policy development, securing land tenure, effective law enforcement, and targeted economic incentives to promote this sustainable agriculture. While the management of land use changes is complex and requires multi-level technical, social, and political coordination, we can begin to address the specific SDG indicators related to forests with remote sensing. Thus, the remainder of this webinar will focus on more of the technical aspects of the use of remote sensing for these goals. So now on to more of this remote sensing information. To track the progress towards the goals and targets, the global indicator framework must capture the multifaceted and ambitious aspirations for the development. Effective reporting of progress towards these indicators requires the use of multiple data types. So both what we have in hand, such as traditional national accounts, household surveys, and routine administrative data, as well as Earth observations. So within the SDGs, there's a clear statement in the text to exploit the contribution to be made by a wide range of data, including Earth observation and geospatial information, while ensuring national ownership in supporting and tracking progress. Since Earth observation and geospatial information are often continuous in their spatial and temporal resolutions, their use in SDG monitoring can be essential for capturing the sustainability of developments. Earth observation and geospatial information can also significantly reduce the cost of monitoring related to the goals and targets. To make SDG monitoring and reporting viable within oftentimes the limited resources available to governments. While there are many differences between data from various remote sensing sources, there are some common characteristics. These include scale and the availability of remotely sensed data for large regions that are sometimes inaccessible. Many satellites have been in operation for a long time, and this assists in our ability to establish landscape baselines and to track changes over time. There are consistent measurements globally that can be easily compared across many regions. There's a diversity of measurements from spectral reflectance that can be used to monitor vegetation health to soil moisture and canopy data. Remotely sensed data can be used in conjunction with field-based estimates, with field-based observations, which serves as a type of cross-validation measurement. And finally, the data are mostly free and open access, and all data available from NASA are free. When using remote sensing data, there are many different considerations and limitations that need to be incorporated into your decision-making process. So first, it's important to think about the region of interest and what you're really trying to achieve. So for example, if you are studying in the tropics, there's often a lot of cloud cover. And in this case, you might need specific types of data to deal with that issue. And there are also many trade-offs, particularly with temporal resolution, and this is how often the satellite measures the same point on the ground, and the spatial resolution, or the level of detail that the sensor can obtain. So additional considerations may be spectral resolution, and this refers to the number of bands within a particular wavelength range. So the higher the spectral resolution, the greater the ability for a sensor to distinguish between different features on the ground. The specifics of these types of resolutions are covered in the fundamentals, so please refer back to that training for these types of questions. Also, the length of the record, the cost of the analysis, particularly for high-resolution imagery, and the future satellite development are all important things to think about. So these are especially important if you are planning to monitor a specific region over a long period of time. There are multiple types of useful remotely sensed data available for monitoring forests. They vary in spatial resolution, temporal resolution, and data type. So we'll briefly discuss some of the attributes of coarse, medium, and high optical imagery, and a little bit about radar imagery. Coarse resolution satellites, generally considered of having a spatial resolution of 250 meters or greater, generally have high temporal resolution. So for example, the MODIS sensor provides data generally on a daily basis. While they're not as useful for identifying small-scale forest changes or forest types, they're often used as an early warning system for deforestation. So they are often used for things like wildfires. One example of an early warning system is the Forest Monitoring for Action, or FORMA, which can be accessed through the World Resources Institute Global Forest Watch. And this helps people managing forests respond more quickly to unwanted forest loss. And we'll discuss the Global Forest Watch in quite a bit of detail later on in this webinar series, particularly in session 3. By utilizing the MODIS data, the FORMA generates alerts in forest clearing activity every 16 days at 500-meter resolution. So the alerts go back all the way to January of 2006 and allows you to see where forest loss has happened and help understand why it's happening. So it's made of several data component types, such as vegetation intensity and VIIRS data from MODIS, precipitation data from NOAA, and historical data on forest clearing. A statistical model uses the individual history of each pixel to identify meaningful signals of forest loss, as opposed to things like drought or seasonal variation. It's often used to identify hotspots of activity that can then be verified by ground data. Medium resolution optical data are most commonly used for forest monitoring, and these include the well-known Landsat and Sentinel-2 satellites. The spatial resolution varies from about 10 to 80 meter pixels. For example, Landsat has a spatial resolution of 30 meters. The trade-off with these data are higher resolution, but less frequent measurements. So Landsat imagery are available every 16 days in the same region, about. Much of these data types have a long record history, which is also really useful for establishing forest baselines. Most are also freely available and available globally. They are limited in terms of temporal resolution, and also the imagery can't be used in areas of high cloud cover. This is particularly an issue in tropical regions that have consistent clouds. An example of a tool that utilizes the medium resolution, again, is this Global Forest Watch, where it is an interactive online forest monitoring and alert system. This system also includes global tree cover loss, a global tree cover loss dataset that was created by Matt Hansen and others using Landsat imagery. So over 1 million satellite images were processed and analyzed, covering 2001 to 2013. So this portal enables you to choose a country or region and inquire information about forest gain or forest loss. You can create custom maps, analyze trends, subscribe to those alerts I just mentioned, or download data for the entire world. So we're going to do a demo of that during session 3. High-resolution data sources can provide more detail than coarse and medium-resolution satellites. However, these data are often only commercially available and are only obtained for very specific regions. Examples of high-resolution satellites are the WorldView 2 and 3 satellites operated by Digital Globe. And these have a resolution of under 2 meters. Other examples include RapidEye, QuickBird, and ICONOS. They provide the benefit of more accurately monitoring forests and can be used for accuracy assessments, sampling transects, or hotspot assessment. When deciding on the use of these data sources, it's really important to consider the costs and the area of coverage, especially if it's necessary to have repeatable, consistent, and continued monitoring of forest changes. Some countries are adopting the use of a combined approach, using both medium and high resolution data. For example, the government of Norway has been working with the government of Tanzania to monitor forest cover change in order to reduce greenhouse gas emissions from deforestation. Although the analysis for the entire country uses Landsat, high-resolution imagery, such as those from Worldview 2, are used in calibration and verification. Radar is an active remote sensing system that utilizes the microwave radio portion of the electromagnetic spectrum and can be used throughout all weather conditions and during the night or the day. One of the most common types of radar is synthetic aperture radar, or SAR. In SAR imaging, microwave pulses are transmitted by an antenna towards the Earth's surface. The microwave energy scattered back to the aircraft is measured. The SAR makes use of the radar principle to form an image by utilizing the time delay of the backscattered signals. In real aperture radar imaging, the ground resolution is limited by the size of the beam sent out by the antenna. Finer details on the ground can be resolved by using a narrower beam. The beam width is inversely proportional to the size of the antenna, so the longer the antenna, the narrower the beam. There are generally two bands used for forest monitoring. The short wavelength, or X-band, interacts mainly with the top layer of the forest canopy, while the longer wavelength radar is able to penetrate deeper into the canopy to undergo multiple scattering between the canopy, the trunks, and the soil. The benefit of SAR is that it can penetrate clouds, which is really useful for tropical areas. It can also provide forest structure data, which can be used in conjunction with the optical data. However, they are often really difficult to process, and you need specialized software to do this. For these reasons, they are oftentimes not used operationally. One particular SAR data product is the global 25-meter resolution forested, non-forested maps. These were generated with images from the Japanese L-band SAR mission, PALSAR and PALSAR 2. The figure here on the right shows an example of forest changes in Borneo in red. Light detection and ranging, or LiDAR, is also an active remote sensing technology that is optical, that discharges tens of thousands of infrared pulses a second from a laser in order to determine elevation values based on the measured travel time of those pulses. When it's combined with GPS, it can collect accurate elevation values with high accuracy. LiDAR is typically collected on planes. Because it's an active sensor providing its own energy source, it can be flown during day or night. However, unlike radar that I just mentioned, LiDAR cannot penetrate clouds, rain, or dense haze, and can only be flown really during periods of fair weather. There are no current LiDAR satellites, so the data can be very expensive to acquire and process. It has the benefit, however, of providing detailed information about forest structure. The image on the right provides an example of the first time an entire country, Panama, was mapped with LiDAR data. So the combination of field data, satellite data, and LiDAR allowed researchers to account for variations in carbon patterns from differences in elevation, slope, climate, and canopy cover. So now we'll talk about some more specific satellites that are relevant to the SDGs. So Landsat is probably the most popular satellite, and I'm sure many of you have heard of it. It was first launched in the 1970s. The data from the early sensors were called MSS, or multispectral scanning imagery. Most recently, Landsat 8 was launched in 2013, And so we have this continuous data at fairly high resolution of about 30 meters, which is really useful for examining land surface changes. All of the data are freely available from the USGS, and it provides imagery of the entire globe every 16 days at a resolution of 30 meters. This table provides an example of each band, the wavelength range for each band, and the spatial resolution, and it compares those between Landsats 4 through 7 on the left and Landsat 8 on the right. Remember, spatial resolution refers to the size of each pixel represented in square meters on the Earth. With the Landsat 8 satellite, there are a few additional bands, such as the coastal aerosol band. There are other bands like the VIIRS band, and there are 2 thermal bands. The thermal bands are collected at 100 meters and then resampled to 30 meters. So sometimes it's hard to visualize what pixel size represents on the ground. So these images show you what a 15, 30, and 100 meters look like relative to a baseball diamond. So the common 30-meter Landsat pixel is about the size of the infield of the baseball field, while the 30 meters are about the square size of from the home plate to the pitcher's mound, and then 100 meters is about the entire field. So for the bands that are 30 meters, you cannot distinguish differences that might occur within that 30 meters. This figure shows the differences in band coverage between Landsat 7 and 8. It also provides some information about this atmospheric window, and these are the ranges where the sensors can obtain the data. Notice that while the band widths are similar between Landsats 4 through 7 and 8, there are some differences. So it's really important to understand these differences when applying the same processes to images from 2 different sensors. There are many different websites where you can obtain Landsat data, and those are listed here. Sometimes it's a little confusing because there are so many sites to find the same type of data. So this is really tends to be what people are most familiar with. So it's a good idea to take a look at the various places and then decide for yourself on how you prefer to view the data and download it. So here we have a few different examples such as Landsat Look Viewer, Glovis Next, the Global Land Cover Facility, and Earth Explorer. MODIS is one of the key imaging instruments for NASA, and it's designed to measure large-scale global dynamics across land, oceans, and atmospheres. So it has 2 satellites. It's flying on 2 satellites, the Aqua and the Terra, and they capture imagery of the same area on Earth just at different times of day. The Terra MODIS passes from north to south across the equator in the morning, and Aqua passes from south to north across the equator in the afternoon. So this allows MODIS to observe any location at least once a day. One limitation of MODIS, however, is its coarser spatial resolution. This figure shows you an example of MODIS tiles, or the area over which the MODIS image is obtained, is much larger than the Landsat. So the MODIS is in blue here, and the Landsat is sort of the brown, pinkish areas. There are also many places to obtain MODIS products, and those are listed here. So we have places like the LPDAC, Reverb, Worldview, Earth Data Search, and the National Snow and Ice Data Center. Another newer satellite that's important for forest applications is the Suomi NPP satellite with the VIIRS sensor on board. VIIRS was launched in 2011, and the spatial resolution is 375 meters or 750 meters, depending on the product. And this has a similar temporal resolution as MODIS. So there are 22 bands measured by VIIRS, and these include visible bands such as red and blue, as well as infrared bands. The near-infrared bands have been particularly useful for identifying things like wildfires. While VIIRS is similar to MODIS, there are differences in the spectral and spatial characteristics, as well as within the data processing and the data delivery. As with MODIS and Landsat products, there are multiple places where you can find VIIRS imagery. One of the most common is Worldview, shown here. There's also the VIIRS Active Fire Mapper, as well as NOAA Class Portal, and the LADS web portal that has MODIS and VIIRS products available. The Sentinels are a fleet of satellites designed specifically to discover the wealth of data and imagery that are central to the European Commission's Copernicus program. Sentinel-2 carries an innovative wide swath at high resolution, so it has 13 spectral bands for land and vegetation. The mission is based on a constellation of 2 identical satellites in the same orbit. Together, they cover all of the Earth's land surface every 5 days, about. Sentinel-2 has a slightly increased temporal resolution and spatial resolution as Landsat. It has a variety of applications and can be used for forest monitoring. So to access Sentinel-2 data, you can use the Copernicus Open Access Hub. And it provides complete and free and open access to all of the Sentinel data. So you can register online, and it's a self-registration process that's automatic. So this allows you to search and download products within the portal and is freely available. So that provides you with an overview of the SDG 15, the importance of remote sensing to meet the targets, and a few of the examples of satellites that you can use for forest monitoring. So now we just have a few minutes for questions, but I wanted to mention that you can email us with follow-up questions. Here are the contact emails for myself and my colleague Cindy Schmidt, as well as our program manager, Anna Prados. And then the ARSET website here is listed at the bottom. So you can type your questions into the question box, and we will try to get to as many as we can. And again, if we can't get to them within our about 7 minutes or so that we have remaining, we will. You can follow up with us later. So thank you for joining us today. And just as a quick reminder, before we jump into the Q&A, tomorrow, we will focus more specifically on that target 15.1, and then we'll have our final session the next day on Thursday that will focus on 15.3. So I'm just going to pull up some of the questions here and see if I can answer any of them for you. And also, as a heads up, if you see a question that maybe hasn't been answered by us, and you know the answer, feel free to communicate with one another. And you could also type in your name, location, and organization and email to connect with some of your potential colleagues that may be on today as well. So I'm just sort of reading through this long list of questions. So give me a few seconds and I'll try to get to at least a couple of them. Okay, so here's a question. Is SWOMI NPP data free? And the answer to that is yes. So that's a joint mission between NASA and the Japanese Space Agency. And all data that is generated by NASA is free. And so the second part of the question mentions comparing MODIS and Landsat, which is better for detecting forest vegetation health. So that's a really good question. And it really kind of goes back to those things I mentioned about temporal and spatial resolution. So with MODIS data, we are able to obtain data almost daily for most regions on the globe, while for most regions Landsat, we're only able to obtain data every 16 days or so. However, Landsat data has a higher spatial resolution, so we'll be able to detect more finer scale changes on the ground. So there are trade-offs here. So MODIS might be better for detecting things like wildfires or rapidly changing conditions on the ground, while Landsat may be better for looking at long-term trends in forests and vegetation health. There are also things you can do, such as the Normalized Difference Vegetation Index, or NDVI, which you can calculate for both of the data from both MODIS and Landsat. And this might give you an idea of the health of the vegetation, either on shorter periods or over longer periods. There is a question here about the Sentinel-2 data used for soil moisture measurements. And because that's an ESA satellite, I'm not as familiar with that one, but I can say that the Sentinel-2 data have been used in conjunction with a NASA satellite called SMAP that is used for soil moisture. And there was a portion of that satellite that is now not operational anymore. So I know that the Sentinel-2 data are oftentimes used for improving the resolution of that SMAP data set. So that probably doesn't totally answer that question, but if you'd like to look for more information on that, you could also look for Sentinel-2 and SMAP, SMAP, or soil moisture active passive. Here's a question. Here's a question about, will you cover GRACE or any other type of gravity remote sensing data? So we will not cover that in this webinar series. There are some other webinars more related to water resources that you can find on our website. We are also having a drought webinar in about a month that will briefly discuss GRACE, but we won't go into any detail of how to use those data. There's another question about, is there a free software for analysis of remotely sensed imagery? Yes, there are a few. One that we have used in some of our trainings is called QGIS, QGIS. And that's really similar to ArcMap, if you're familiar with those. But it does have some nice plugins for analysis of remotely sensed imagery and conducting classification. There's also another program that I'm not as familiar with called Multispec that I know my colleague Cindy Schmidt has used, and I believe that's a freely available one as well. Another question about, are MODIS products available through web services? Yes, so you can find MODIS products. Another good one that we didn't talk much about for MODIS, but we did mention briefly, is Earth Data Search. So if you kind of just Google NASA Earth Data Search, you'll be able to find that website, and you can find different types of MODIS products available there. And the NDVI, which I mentioned previously, is one of those examples of one of those products there. I'm just reading through some of these as well, and I think we're pretty close to time, so maybe I'll try to find one last question we can answer. And if you still have questions, feel free to email us or ask some of your colleagues as well. So there's a question about getting technical support to use NASA data. And I know that with some of the DACs, so these are the data portals for which you can access NASA data, have some type of help system set up in terms of accessing the NASA data. And in terms of utilizing the imagery and conducting analysis, I would recommend seeing some of our more advanced webinars that we have on the ARSET website. So I think we are about at time, actually a couple minutes over time now. So I just want to thank you all again for being here today, and I'm looking forward to our next two lectures that we will have tomorrow and Thursday. And again, feel free to post your information if you'd like to connect with your colleagues, or email us with more specific questions. So thank you all, and we will talk to you tomorrow.